Algebra 2, Concept 5. We're going to go through notes on how to solve three-variable systems algebraically, so both by elimination and substitution. I'm going to be covering a lot of material very quickly, so you'll probably want to pause your video often so that you can get these notes down. So first we're going to talk about solving by elimination. So with the three-variable equation system, we use the variables x, y, and z. And if we have three variables, then we need to have three equations. So we can have three different solution situations like with a linear system. So we can have one solution, infinitely many, or no solution. So look at the steps. The first thing we're going to do, solving by elimination, is we're going to rewrite the linear system by grouping the first two equations together and the last two equations together. Then we're going to choose one variable to eliminate in both sets of the equations. If it's not the same variable in each set of equations, then it will not work. So I'm going to choose to eliminate the x. So I'm multiplying the second equation on the left by 2 and the top equation on the right by 3. So then you'll see we'll have our two equations, and I'm going to, with the pair on the left, I'm going to subtract. And I have to subtract each set of variables. So I end up getting 8y minus 7z equals 29. Over on the right, I'm also going to be subtracting because my x variables are the same. So I get negative 8y plus 11z equals negative 41. I've just completed step 2. Now step 3 is I'm going to group these two variable equations together and solve. And I'm going to do that on my next slide. So I have grouped the two together, and these are all set up to eliminate. So I'm going to add, since my terms here are opposite. So I get 4z equals negative 12, or z equals negative 3. Now I'm to step 4, so I'm going to substitute the value. Sorry, I'm still at step 3. So I'm going to take z and plug it into one of my equations just here in this system and solve for y. So I have plugged it into the top equation and I get that y equals 1. Now we're ready for step 4, where we take the solution from the two variables and plug it in to any one of the original equations to solve for the third variable. So I chose to plug it in to the first one. So I'm plugging in values for y and z here, and now I'm going to solve for x. So my final solution, and I write it as an ordered triple, x, y, and z. So 2, 1, negative 3. So that means that this system has exactly one solution. Let's look on how to solve a three-variable, three-equation system using substitution. So I'm going to choose one equation to solve for one variable. So I have chosen the top equation and I'm solving it for y. So you can see I have that y equals 2x minus z minus 15. Now, step 2, I'm going to substitute the solved expression into the other two equations. So I'm going to substitute it into these two equations. So with the top one, I substitute in for y, and I simplify, and I get this equation. And then I substitute it in the bottom equation. And now, this is my second equation here. Step 3 is we take these two variable equations and set up a new system, just like we did with elimination. Now I look at these and I decide that I'm going to multiply the top one by 7 and the bottom one by 3. And I'm going to eliminate my z's. So I end up getting x equals 5. So now step 4, I'm going to substitute, I'm still on step 3. I get ahead on this step. Is I need to take this value for x and put it up into one of these original equations to solve for z. There. Now z equals negative 5, and I'm on to step 4. So I'm taking my value for x and z's, my values, and going to plug them into an original equation. So I chose the last equation. And then I get 0. Now to check your ordered triple, you should plug it into each of the three original equations, and it should make 3 true statements. So let's solve this system, and I'm going to show you a system that has infinitely many solutions. It's like when you solve just a two-variable linear system. You get a true statement like 0 equals 0. So you can decide, do I want to solve this using elimination or substitution? I decided to use substitution, so I solved the top equation for x. And now I'm going to solve this, substitute this expression into these two equations below to make a new system. So I substituted it into the second equation and I get z equals 0. And then I substitute it into the third equation and I also get z equals 0. Now we're going to keep going with our steps. So I combine those two equations to solve. And then I can just eliminate. I'm going to subtract. So I end up getting 0 equals 0. So don't stop when you get strange answers like this. Just continue with the process. And then when you get 0 equals 0, that means that this solution has this system has infinitely many solutions. Now let's look at a system when you solve it's no solution. So we're going to get an untrue, a statement that's not true when we solve this. Again, make a decision as to whether you want to solve using substitution or elimination. I decided to use elimination, so I grouped the first two, and I multiplied the top by 2, and I noticed that all of my variables eliminated. And I stopped, because then when I get at any point in the process a statement that is not true, that means that these systems, and they end up, when you graph them, it's a plane, it's not a line, that these planes are not going to intersect. Okay, so let's look at this real life problem. So an amphitheater charges, it should be charged $75 for each seat in section A, $55 for each seat in section B, and $30 for each lawn seat. There are 3 times as many seats in section B as in section A, and the revenue from selling all 23,000 seats in the amphitheater is $870,000. How many seats are in each section of the amphitheater? Well, right away you can see that we've got 3 unknowns, section A, section B, and the lawn. So I'm going to let my variables, anytime you have a real life problem, start by setting up your variables. What's your unknown? So I'm letting A be the number of seats in section A, B being the number of seats in section B, and capital L the number of lawn seats. Now I'm going to go back and read through this situation and set up 3 equations. So my first equation is just the total money revenue that's involved. I was told that section A seats are 75, so 75 times A will give me the money generated for this section, 55B plus 30L, and this together is going to equal this amount. I was also told that there are 3 times as many seats in section B as in section A. So to make them equal, I have to multiply section A by 3. Finally, I was told, just subtly, that there are 23,000 seats in the amphitheater. So I can simply just add up the number of seats and have that be a total. Now I have to decide, do I want to solve this using elimination or substitution? I'm going to use substitution because right here I have B equals 3A. So I'm going to substitute that into my top and my third equation for B. And so then I'm going to get a new system. So I'm going to multiply here and combine my A's. So I get 240A plus 30L equals 870,000, and 4A plus L equals 23,000. Now I can solve this 2-variable system. I am going to eliminate. So I'm multiplying the second one by 30, and then I will subtract so that my L's here terms, these will eliminate. So I get 120A equals 180,000 because I have to subtract these amounts as well. Divide, so the seats in section A is 1,500. Then I can substitute that in to the equation where B equals 3 times A. So in section B is 4,500. And then I substitute that into, I'm just going to put it into this equation up here because I know what A is and find out that there are 17,000 seats in section L. Again, I went through a lot of information very quickly, so hopefully you paused quite a bit to get down the writing and to soak in all the math work that I have done to make sure that you understand. If not, go back and review this video so you can make sure that you understand how to solve a 3-variable 3-equation system.